Tanita Ramburuth-Hurt. I'm a final year PhD student at the University of Geneva. And today I will be presenting my current work and work that I've done previously during my PhD, basically on the topic of investigating the chemical diversity of gas and galaxies, from galaxies at high Z to back home to the Milky Way. So before I go into the science, I thought it'd be nice to just introduce my department a little bit. So the University of Geneva is based in Switzerland. The Department of Astronomy is in a forest just outside of the city of Geneva. So every day I get to walk through a forest, which is kind of nice, unless it's snowing, because then it's very cold. But so within the Department of Astronomy, I'm part of the Galaxies in the Universe research group, which has 4 subgroups, which are starbursts in the universe, galaxies of cosmic dawn, searching for sources of cosmic ionization, and then gas, metals, and dust in galaxies. And that's the group that I form part of. Okay, so gas and galaxies. Why is this important? So gas is a fundamental ingredient of galaxies because it forms the fuel for star formation. And when we study the gas in galaxies, we can study galactic gas cycles and the interaction of the ISM with the CGM. So this is some of you might be familiar with this image from Tunis in 2017, which is an artistic interpretation of gas cycles in a galaxy. So you can see in the middle there, the galaxy is quite small compared to the gaseous environment. And what we see is we have accreting gas onto the galaxy from outside. We have gas being recycled. We have gas outflowing from the galaxy. And all of this sits within a diffuse gas medium. And so studying the metallicity of the gas in galaxies gives us insight into the chemical evolution. And in particular, what we expect of these gas flows in terms of their metal content is that we have outflows potentially being more metal enriched because they've been processed by the stars, and then the inflows of the gas potentially more metal poor or pristine coming from outside in the circumgalactic medium. And so studying the metallicity of the gas in galaxies can give us a lot of insight into how the gas moves in and around the galaxy and how that contributes to the evolution. So in my work, I study the gas in galaxies using absorption-line spectroscopy. And that is where we have a bright background source. So if it's external galaxies, it's usually a quasar. But if we're inside the galaxy, the Milky Way, then the background source is generally a very bright star. And so the light from this background source travels through the intervening medium until it reaches us here on Earth. And the metals in the gas absorb at certain signature frequencies or wavelengths. And from this information, we can know very well the metals that are in the gas, as well as how much metals are in the gas. So this is a very powerful method that we can use to determine the chemical composition, the metal content of the gas that we are probing. And then further, if we have very high resolution spectroscopy, we are able to study individual gas components along this line of sight. So this is just a loose sketch where we have the bright background source traveling through, say, 3 different gas components or gas clouds along the line of sight, each potentially with different chemical enrichment properties, but they're defined by having different velocities. And so what we see in the absorption profile is these nice kind of dissected absorption line profile for each metal. So for example, here we have iron that's wavelength the wavelength of 2249 angstroms. And so each of these kind of individual lines corresponds to each of these individual gas components. So this is a very powerful thing that we can do with very high resolution spectroscopy. We can study the line of sight, not only the full line of sight, but gas clouds along the line of sight, and we can compare them. So just as a cute analogy, if we have the whole line of sight as this calico cat on your left, dissecting the line of sight would mean taking apart the components and getting what the cat is made of. So we have an integrated cat line of sight and its individual kitten components. Okay, so the main caveat that we have with this method is that we can't measure the total metallicity of the individual components, and this is because of the damped and saturated H1 absorption line. So as an example, you can see that it's not possible to identify these nice individual gas components within the absorption profile of the hydrogen. But what we can do is we can measure the level of dust depletion using the relative abundances of metals and use this as a proxy for chemical enrichment. So now I'll go a bit more into what I mean by dust depletion. So basically we have metals that are missing from the gas phase, and this is due to this phenomenon called dust depletion, which is where the metals become locked into dust grains and are therefore no longer observable in the gas phase. So this is a plot from this paper in 1996, where we have on the x-axis the condensation temperature of a metal, and then on the y-axis its abundance with respect to hydrogen. And you can see that zinc is much less depleted than iron, for example. And so we can measure, if we measure the relative abundances of these two metals, we can trace how much dust is in the gas. Okay, so now the way that we characterize dust depletion is using this method where we apply metal patterns. So on the x-axis is the refractory index, and that is an indication of how easily a metal forms dust. So the more refractory elements form dust quite easily, whereas the volatile elements merely stay in the gas phase for a bit longer. And so we can plot the refractory index against the equivalent metal column density described by this equation. The only important thing about that equation is that it doesn't include the hydrogen, as I said before. So for individual components, we don't have the hydrogen. And then we can plot for each metal, and if we have no dust depletion, then the metals line up horizontally more or less, and we can fit a straight line, and the is the depletion factor. So in this case, we'd have a depletion factor of 0, which means we have no dust depletion. But if we have then a system with a higher level of dust depletion, the refractory metals become locked into dust grains and we lose them from the gas phase. And so we can fit a straight line again to this, and the depletion factor would be greater than 0. So in this case, we have high depletion because we have a higher slope or a larger value for the slope. So in real life, these obviously don't always line up very nicely like this. And we can get these deviations from this straight line. And that can be due to things like nucleosynthesis effects and ionization effects. And that's kind of a strong advantage of this method, is that metal patterns are sensitive to nucleosynthesis and ionization effects. And we see this, we see nucleosynthesis in the form of the enhancement of alpha elements and an underabundance of manganese. And then we can see evidence for ionization by an overabundance of sulfur. And I'll talk about that a bit more later. So dust depletion can be used as a proxy for chemical enrichment if we have a very wide range of metallicities. So this is a figure that I'm showing from the CHIA 2016, where we have on the x-axis the metallicity in terms of zinc, and then on the y-axis we have a measure of the dust depletion. And so for DLAs, we do see a general trend of increasing metallicity with dust depletion. But when we look at the Milky Way, which is in orange, there's a much bigger scatter. And that's because metallicity also depends on temperature and density. And so although it can be used as a proxy for chemical enrichment, dust depletion is not always a direct trace of it. So that's just to keep in mind. Okay, so that's a bit of an introduction to the methodology and how the work that I do fits into context. So now I'll present some the results from my first paper, which was on chemical diversity in distant galaxies. So the metal and dust enrichment and variations within absorbing galaxies between redshifts 1.7 and 4.2. The galaxies that we studied were diamond, slime, and oxide absorbing systems, or DLAs. So these are gas systems with hydrogen column density greater than 10 to the 20.3 centimeters squared. So this is a image from a simulation from this paper in 2020 showing the projected H1 column density. And the DLAs are situated in the most dense or part of this gas system. Sorry, of this gas system. So a challenge with DLAs is that only 10% of them have emission counterparts. So we see only, for a lot of them, we only see them in absorption. But they've been shown to be associated with galaxies, galaxies with masses between 10 to the 6 and 10 to the 11. So we do strongly believe that these DLAs are galaxies. Yes. So studying DLAs when we study DLAs in absorption, we can see the smallest and faintest galaxies at high redshift. And we believe that these are the most numerous galaxies in the universe. So it's very important for us to study them to fully understand galaxy evolution. Yeah. So in this work, we studied the chemical enrichment and variation using dust depletion as a proxy for a sample of 64 DLAs. And this is the first result that we have, which shows diversity of chemical enrichment in DLAs. Oh, so what I show here is on the x-axis is like the list of our DLAs named by their quasar, and on the y-axis is the depletion factor. And you can see that in several of our systems there is a range of depletion factors. So that's, you can see vertically. Yeah. So we also looked at the depletion factor with respect to redshift. And what's interesting about this plot is that we see, so even at low redshift, at redshift around 2, we see these gas systems with very low depletion, 0 depletion. And this is interesting because it could mean that we are probing more the pristine or the metal poor circumgalactic medium instead of the metal enriched ISM. Yeah. So the second result is that we see evidence for nucleosynthesis effects, as I mentioned earlier. So this refers to an over and underabundances of certain metals due to their formation processes. So more particularly, core collapse supernovae produce the alpha elements, which are, for example, silicon, magnesium, sulfur, and oxygen. And the iron group metals and manganese are produced by type 1a supernovae. And in general, core collapse supernovae happen about 1 giga-year before we see type 1a supernovae. So earlier in a galaxy's life, in general, we might see this alpha element enhancement whereas we might see an underabundance of manganese. Yeah, so this is what we saw. So we see evidence for nucleosynthesis effects. So here I'm showing the depletion factor on the x-axis and the relative abundance with respect to iron as a deviation from the straight lines to the metal patterns. So my work is the black dots, and overplotted are the nucleosynthesis taken from stars. So we can see that we do see this overabundance of the alpha element silicon, for example, and this underabundance of manganese, which has a lot of information on the nucleosynthesis that's happening in these galaxies. And then the third result is possible hints for outflowing gas. So that for this we combined the velocities, so the kinematics, and their chemical enrichment. So on the x-axis is the velocity of the individual components, and then on the y-axis is the depletion factor. And this is for this was my favorite DLA for this project, because it had so many components. So for example, component number 3 has both high depletion and high relative velocities. And we wonder whether this could be hints for an outflow of chemically enriched gas. But this is very difficult to say for sure because we don't know the morphology of these galaxies. So we can't know precisely the movement of the gas clouds in relation to the center of the galaxy. So this is a difficult conclusion to draw. But it is an interesting way to look at starting to pave the way to getting these kinds of results. Okay, so I'm going to bring it back home to the Milky Way. And this is the project that I'm currently working on. So the results here are very preliminary. But yeah, so the project is investigating the chemical diversity of ISM in the solar neighborhood. And the open questions that we are trying to answer are whether the neutral gas is chemically inhomogeneous, and if it is, how large are the variations in its depletion or its metallicity. So this is a literature compilation of 3 different papers. So Ricci et al. 2023, Ricci et al. 2021, and then the general metallicity gradient taken from this paper based on H2 regions. So what's important to note from this plot is that the Ricci paper and the Diccia paper are both probing the same type of gas, so the neutral gas. But one paper finds very small variations in the metallicity, while the Diccia finds much larger variations in the metallicity. So this project is based on trying to find where the level of variations really lies. So the data for this comes from a recent HST program where we targeted 8 stars within 2 kiloparsecs of the sun, and we got very high resolution spectra, and then based our observations around getting the absorption lines for these metals and others, so that we can get a large range of the depletion factors. So the subsample was taken from Diccia 2021, and the selection of these targets was motivated by seeing an upturn in the abundance patterns, which could indicate having a mix of gases with different metallicities along these lines of sight. And the second criteria was that they have complex absorption profiles, which indicates multiple gas components along the line of sight. So this is a map of the targets that we chose. And so what I'm going to show you now is preliminary results for one of our targets. the spectra for Kappa Aquilae looks like this for three different ions. And what I want to show you here is the vertical dotted lines show the location in relative velocity of different components that we see in these absorption profiles. And this was done by Voigt profile fitting, but it's important to note that the solution to Voigt profile fitting is not unique. So this is an iterative process that we do, and often we need to combine adjacent components to get more constrained quantum densities for these metals. Okay, so for this target, we were able to measure the amount of depletion for individual components along the line of sight against its velocity. And so the preliminary result that we see here is that we do see variations in depletion. So you can see there's quite high depletion and quite low depletion just along this one line of sight. But again, whether this implies a variation in the metallicity is still not super clear. And that's because we can't calculate the metallicity. But what we can do is we can obtain an allowed range of metallicities for individual components if we consider possible distributions of the hydrogen gas. So if we make an assumption on how the hydrogen gas is distributed along the line of sight, then we can calculate the metallicity. So this is, for example, we've assumed that the first component has 10% of the hydrogen gas. The second component also 10%, the third component 50%, etc. And so this is what we would get for the metallicity if we assumed this particular distribution of hydrogen. And we can do that for several distributions. Several distributions. And what we can eventually get is kind of this range of the allowed metallicity for each component. And preliminarily, we see that the metallicities only overlap partially for these components, which indicates a diversity of the metallicity along the line of sight, up to 0.5 dex. Yes. So a possible future endeavor with this project would be a synergy with 21 centimeter H1 radial maps of the Milky Way. Because if we are able to get the hydrogen quantum density for individual components from 21 centimeter maps, we will be able to further constrain the metallicities of these individual components. But I'm not a radio astronomer, so if anyone is very familiar with galactic H1, please come and see me. Okay. So in summary, studying galaxies by studying their gas content and absorption is a very powerful method for obtaining information on the chemical enrichment of galaxies. And then further, with high resolution spectroscopy, we can study lines of sight on a component by component basis. And then from my first paper, we find that several DLAs in our sample are chemically diverse. We present evidence for core collapse supernovae nucleosynthesis effects in distant galaxies. And then in combining the kinematics and chemical enrichment of these galaxies, we can start to look for evidence for outflowing chemically enriched gas. And then back home to the Milky Way, I presented here preliminary results that show variations in dust depletion towards one of our targets, Kappa Aquilae. I've shown that metallicity for individual components is difficult to constrain, but there is preliminary evidence for component-to-component variations up to 0.5 dex. And then for this project, we hope to constrain dust depletion, ionization, and metallicity for all of our 8 lines of sight. And that's all. Thank you very much for having me.
Okay, thank you so much. Any question online? Yes, Rebecca.
Thank you for very, very nice. I wanted to ask sort of something that's perhaps a bit tangential to what you're doing, but that fluffy sort of artist's impression you showed of gas flowing by the galaxy.
Yes.
So that's the slow sort of stuff that's going on all the time, right?
Yes.
But is it not true that at some point this galaxy becomes an AGN and it just spews out a ton of gas? Is the AGN phase not more important in the end than the less romantic part of its life?
I don't know really. I haven't studied AGN, but I guess the outflows could be due to AGN activity, but yeah, I'm not really sure.
Okay.
Sorry.
Yeah, I'm just wondering about rates compared to just I don't know some winds like thing.
Right. Yeah, I'm not sure. I don't know too much about AGN.
All right.
Okay, any more questions also online? Let's see. I just have like a more general question. I think it was slide 37 or 36. I don't know. Can you explain a bit more about this, the H1 density distribution?
Yeah, so we can't calculate the metallicity of individual components because of the saturation of the absorption line for hydrogen. But we know the total hydrogen along the line of sight, the column density. So we can make assumptions on how much of the gas is in each component. And
so
then
this 115, 12, they're just your assumptions.
their assumptions, yeah. So and yeah, so 10% is the amount of hydrogen in the relevant components. But obviously there's like so many different combinations and permutations of this we can do.
Yeah.
And that's what I'm generally giving the idea of here. And then if you do it for many different combinations and permutations, then you can get like a maximum and a minimum.
Okay.
Yes.
Yeah, okay. If there are no more questions, then let's thank Tanita again. Thank you everyone for that one. And hopefully we will see you in our next colloquium, which will be next week, next Thursday at 11. Thank you.